Hi everyone, in this video I'm going to give you a brief introduction to a powerful surface analytical method called as time-of-flight secondary ion mass spectrometry, in short referred to as TOF-SIMS. Let us begin by understanding the working principle of SIMS. In general, most of the analytical methods either involve electron beam, X-rays, or ion beam. In SIMS, as the name suggests, we are interested in ion beam to do our analysis. When energetic ions impinge material, different interactions between surface and ion beam can take place, resulting in elastically or inelastically scattered or recoiled incident beam, aka secondary emission pattern. In addition to release of characteristic X-rays, photoelectrons, backscattered electrons, etc., an incident beam may cause ionization of the sample. In SIMS, we monitor these secondary ion species. This technique represents the most sensitive surface characterization technique developed to date, with detection limits of 10^10 to 10^15 atoms per centimeter cube, that is 0.1 parts per billion to 0.1 parts per million. It has ability to detect or quantify any element in periodic table. In contrast to common bulk ionization methods like electron spray ionization or matrix-assisted laser desorption, SIMS analyzes samples in their native state without the need for a suitable matrix solution. As a result, SIMS is the best choice to characterize organic-based thin films and polymer surfaces. Let us now look at the operating principle of TOF-SIMS instrument. Broadly speaking, there are three main components in the instrument. First is the ionization chamber, where the sample surface is bombarded with primary ion beam, resulting in emission of secondary ions. Second section is the TOF mass analyzer, which separates different masses based on their time of flight. Third, at last, the species reach the detector, and then we can get mass spectrum, giving us the detailed information about the molecular structure of the surfaces. So this is our sample showing the top few layers of atoms. Here we have high energy ion source with energy from 1 to 30 kilo electron volts directed onto a sample surface. The absorption of this energy by the top 50 angstrom of the sample results in the sputtering of neutral and charged species, positive and negative, from the surface. We see neutral atoms and atomic clusters and charged molecular fragments. Depending on the desired species to be analyzed, a variety of primary ion beams may be used, such as cesium positive, oxygen argon positive, and gallium positive. Titanic primary beams like cesium positive is used to ionize electronegative elements, example oxygen, carbon, nitrogen, halogens, chalcogens, and oxygen atoms are used to ionize electropositive elements, example lithium, magnesium, etc. Liquid metal ion beams like gallium gold are used for high-resolution studies, where the beam can be focused to a smaller diameter of less than 50 nanometer. The next phase of these secondary charge species is the TOF mass analyzer. Before we go into how TOF mass analyzer work, we should note here one thing, that primary ion source is always pulsed, where each pulse of primary ion beam produces a full spectrum of secondary ions. Hence, the highest mass resolution is afforded by using the shortest pulse of primary ion, since the time of flight for ions may be determined more precisely. Here is the time of flight mass analyzer chamber. An ion of known electrical charge but unknown mass is accelerated by an electric field. As a result, all ions of the same charge will have identical kinetic energies. However, the velocity of the ion will depend on the mass to charge ratio, which affects the time it takes for charged species to reach the detector. That is, lighter ions here shown in purple will reach the detector before heavier blue mass species, allowing for effective mass separation and analysis. If the length of the flight tube is given by capital L, then the velocity of species small v will be equal to capital L by time t. By conservation of energy, kinetic energy is equal to potential energy. The potential energy is given by charge z times the acceleration potential capital V, and that will be equal to half mv square. On substituting the earlier relation, we finally get the relation m over z is proportional to time square. By measuring the time of flight, we can now get information about m by z value and get a mass spectra. The time of flight analyzer is advantageous over other kind of mass analyzers like quadrupole. This is because it allows the parallel detection of all masses and thus giving us higher mass resolution. Another thing is that since the secondary ion yield is not directly corresponding to the abundance of the elements or molecules on surface, this method is not quantitative. This is a typical TOF-SIMS mass spectra obtained in positive and negative ion mode. There are two varieties of SIMS, static and dynamic. Modern-day TOF-SIMS is capable of doing both modes. Static mode is when there is controlled sputtering mode, where the entire analysis may be performed without removing less than 1/10 of an atomic monolayer. This is useful for surface and elemental analysis or imaging of the top 2 to 3 monolayers of a sample. It does not appreciably deteriorate the surface being analyzed. In comparison, dynamic SIMS is used to determine elemental concentrations of the sample as a function of depth. Dynamic SIMS is a destructive technique primarily used for depth profiling. To summarize, time-of-flight secondary ion mass spectrometry is probably the most sensitive analytical method for solid materials. We can get not only the mass spectra but also do 3D mapping and get depth resolution. Thank you for watching the video.